All right, well, welcome back, everyone. Let's go ahead and get started with today's video covering source transformation and superposition. So I hope during today's video you will see that source transformation and superposition are two very useful tools that can help take an ugly circuit and turn them into something quite a bit more manageable. So here's our goals for today. First, we're going to learn how to use source transformations to simplify and analyze our circuits. We'll also learn about superposition, and we'll see that superposition makes it a lot easier to analyze circuits that contain multiple sources. We will also learn that both source transformation and superposition require our circuits to be linear. Most of the time in our class, our circuits will have linear behavior, but we'll also review how do we determine whether our circuits are linear. If you happen to have a circuit with nonlinear behavior, then you may not be able to use source transformation or superposition. So we'll also clear up how to make sure everybody's linear before we perform that analysis. So let's go ahead and do a quick review question before we jump into the new material. So here we are being asked to write the mesh equation for the mesh I1. So you'll remember in our previous video, we learned about how to write mesh equations. Let's briefly review. So remember, when writing a mesh equation, you want to apply Kirchhoff's voltage law. And then you want to rewrite each voltage in terms of the mesh currents and resistances. So let's go ahead and apply Kirchhoff's voltage law. So I'm going to start in the bottom left corner of my circuit, and I'm going to walk clockwise around my circuit. And remember, I want to make sure that I apply a consistent sign convention. So here, the first thing I walk across is that 1 volt source. So based on my convention, I'm going from a minus to a plus, so I am going to be gaining plus 1 volts when I walk across that source. Next, I'm going to walk across this resistor. And notice that the current and the direction I'm walking are the same. So in this case, I'm going to lose 100 volts, or I'm going to lose this voltage drop across my 100 ohm resistor. So I'm going to say minus V100 ohms. That's the voltage drop across that 100 ohm resistor. Finally, I walk across that 10 ohm resistor, and once again, notice the current is also assumed to be entering the top end of this resistor. So in this case, I'm going to treat that as a voltage drop, and I get this Kirchhoff's voltage law equation. So I just need to rewrite my V100 and my V10 in terms of the mesh currents and resistances. So let's see what we get. Let's first consider the 100 ohm resistor. So for that resistor, I know that I have current I1 flowing from left to right. And notice in the mesh above this I2 mesh, I also have I2 flowing from right to left. So remember, it's important that we correctly capture the true amount of current going through that 100 ohm resistor. And if I apply Kirchhoff's current law, I can determine that the current through my 100 ohm resistor must be equal to I1 minus I2. At least that is my net current moving from left to right. Therefore, my voltage drop across a 100 ohm resistor must equal my resistance, which is 100 ohms, times I1 minus I2. So 100 ohms times the net current flowing from left to right. We can use a similar approach for the voltage across the 10 ohm resistor. So notice for this 10 ohm resistor, notice that we care about the voltage heading in that downward direction. And in that direction, we have current I1 moving downward and current I3 flowing in the opposite direction. So what will my net current in the downward direction be for that 10 ohm resistor? You should find, by Kirchhoff's current law, or by drawing the picture, you should determine that the voltage drop across that 10 ohm resistor is equal to our 10 ohm resistance times I1 minus I3. So therefore, we can substitute these two voltages back in. And we end up with our final mesh equation. So we substitute and we determine we have plus 1 volt minus V 100 ohms, which is 100 times I1 minus I2. Then we have minus V 10 ohms, which is 10 times I1 minus I3. That is our mesh equation for I1. And if we wanted to fully solve this circuit, we would need to repeat those same steps for meshes I2 and I3. We'd end up with 3 equations, 3 unknowns, and we could solve for those mesh currents. In this question, we only needed to find the mesh equation for I1, so we go ahead and end at this point. Okay, so now that we've reviewed our mesh analysis, let's just remind ourselves briefly of all the tools we've covered so far. So please keep these equations handy. You'll find that we are going to be using Kirchhoff's laws and Ohm's law and all of these tools throughout the semester. So keep these equations handy. I highly recommend that you prepare a running formula sheet to keep track of everything. Also remember, we covered our different toolbox equations, including sign conventions. Notice we also covered node analysis and mesh analysis as new tools. So keep these handy and make sure you start practicing using all of these tools on the homework and, if needed, additionally on your own. We'll continue to use these tools all semester long. Alright, so now that we're done reviewing, let's just take a quick preview of where we're headed next. So as I mentioned, in today's video, we're going to focus on source transformation and superposition. This video is part of the next 3 lectures where we're working on finding more ways to simplify circuits and make our lives easier. So today, our focus is on superposition and source transformation. And then in our next videos, we're going to look at circuit theorems, including Thevenin's and Norton's theorem, and finally, maximum power transfer theorem. For this video, let's focus on the first 2 items. So you may remember I mentioned earlier that in order to use any of these new tools, including superposition source transformation, so any of these tools require our circuit to have linear behavior. So all 5 of these tools require our circuit to have linear behavior. And the good news is, most of the time in this class, our circuits are going to have linear behavior. But let's just briefly review what that means. What does it mean for a circuit to be linear? What do we need to watch out for in cases where circuits do not behave linearly? Let's take a look. So here's the definition. A linear circuit is a circuit whose output is linearly related or directly proportional to its input. So when we say linearly related or directly proportional, what we mean is that if the input increases by a factor of k, then the output must also increase by the same factor k. So, for example, suppose we have some circuit element and suppose I input a current I equals 2 amps. Suppose I know that if I'm inputting 2 amps of current, I'm going to get 10 volts across that circuit element. If my circuit has linear behavior, then what we'll see is that if I change my current to 4 amps, then our voltage will also proportionately double. So notice if we double the input, we will also double the other outputs. So this is an example of a linear circuit. Everything increases proportionally. If we increase our input by a factor of 2, the output will also increase by a factor of 2. So why does linearity matter? We're going to see in today's class that circuits having linear behavior allows us to make some very important tools. First, linearity allows us to use superposition. We'll see later in this video that it allows us to consider the effect of each source separately. We can add multiple sources together to determine what the cumulative effect will be. The second thing linearity allows us to do is to use what's called equivalent circuits. These are things like source transformation, which we'll talk about today. And this also enables us to do things like Thevenin's and Norton's theorem. We'll learn about these later. So Notice if we want to be able to use equivalent circuits and replace one circuit with an equivalent other circuit, we need to have linear behavior. So how do we tell if a circuit is linear? So one of the first ways to check is to compare the input and the output. If we increase our input by a factor of k, the output of our linear circuit will also increase by a factor of k. If not, the circuit is nonlinear. So one example of this, suppose you had some voltage. Remember we talked about Ohm's law, right? Suppose our voltage is given by Ohm's law, V equals IR. In this case, if we increase I of t by a factor of 2, then we would see that V of t would be equal to 2 I of t times R, and V of t also doubles. But if for some reason we had an unusual circuit element where voltage was equal to current squared, then notice if I of t doubles, V of t actually increases by a factor of 4. So if a circuit element had a behavior like this would be considered nonlinear behavior. So make sure you pay attention to that difference. So one way to tell if a circuit is linear is to check input and output just like this. And again, if both the input and the output will increase by the same factor of k, then we see linear behavior. Another way to tell if a circuit is linear is to check what components the circuit contains. It turns out, if we have a circuit that contains only the following elements, that circuit will also be linear. For example, if a circuit contains resistors, capacitors, inductors, and linear dependent sources, that circuit must have linear behavior. Notice when we say linear dependent sources, what we mean is that the expression here is a linear thing. Notice if I doubles, 10I will also double. An example of a nonlinear dependent source would be something like this, where we had our dependent voltage source with 10I squared. Notice I squared would produce nonlinear behavior. So as you can see, the vast majority of the time in our class, our circuits will have linear behavior. But keep an eye out because occasionally there may be situations when a circuit has nonlinear behavior. All right, so now that we know whether to determine things are nonlinear versus linear, let's go ahead and start reviewing these new tools. So once again, all of these tools require that we have a circuit with linear behavior, which for the vast majority of the time in this class, that will be the case. So let's start out with source transformation. Source transformation allows us to replace a voltage source and series resistor by an equivalent current source and parallel resistor. So this might seem a little crazy, right? I mean, how often do people tell you you can just change a voltage source and a series resistor to a current source and parallel resistor? Or we can do the reverse. Notice the word equivalent here. That is the key thing. We are only allowed to replace a voltage source and series resistor with a current source and parallel resistor if that current source and parallel resistor is equivalent. So let's go ahead and take a look at, first of all, how and why is this even possible? And let's also look at sources and what it means for sources to be equivalent. So just a bit of review. You may remember we talked about ideal current and voltage sources. And we learned how an ideal current source can basically provide infinitely high energy so that it will always supply the exact current specified. An ideal current source will always give you the specified current no matter what is attached to it, no matter how high of current you're asking it to provide. Of course, we know that in real life, real current sources can only provide so much voltage and so much energy before they max out. Similarly, an ideal voltage source supplies enough current so that it will always provide the same voltage. So it will always have enough energy. It will always be able to provide enough current to give you that voltage V of t. But as we mentioned, in real life, voltage and current sources cannot have truly ideal behavior. We can have close to ideal behavior, but eventually we're going to max out or saturate, and we will see that we cannot have infinite energy and infinitely powerful sources. So one thing we often do to model a non-ideal voltage and current source is we take the ideal source and we add a resistor. Notice that for the non-ideal voltage source, the voltage that we are able to provide across the source's inputs, let's call it A and B, the voltage supplied by this voltage source will gradually decrease as we supply more power. And so basically this resistor, it limits the maximum current that we can produce. So it allows the voltage source to have more realistic behavior. We can only supply so much voltage, so much current before we max out. We use a similar approach to model non-ideal current sources. Notice that this current source will need to supply some voltage, just like how this voltage source needs to supply some current. And so we see that there's only so much voltage we will be able to provide due to that resistor. Once we provide so much resistance, we will eventually saturate and max out. So the parallel resistor will limit the maximum amount of output we can produce. Okay, so we reviewed sources and we reminded ourselves kind of what not ideal and non-ideal behavior looks like. But how do we know for sure if something is equivalent? So in the circuits lab, what we typically do is we use something called the IV curve. The IV curve tells us the behavior of a circuit or a circuit component across a range of voltage and current conditions. It's kind of like taking somebody's fingerprints, and you can basically see how that circuit uniquely behaves under given conditions. And so the idea here is that if we have two circuit components that have the same IV behavior, those components are equivalent. Remember how we replaced series resistors with equivalent resistors, and we saw the same approach is going on here, right? If we know that two circuit elements have the same voltage current behavior, we can legally replace, for example, two 5-ohm resistors in series with a single 10-ohm resistor, because we know that the voltage and current through either of those components would be identical. So, key takeaway here, if two components have that same IV curve, they have the same behavior over the range of voltages and currents, then those two circuits or components are considered equivalent. All right, let's look at an example. Suppose we were to measure some test circuit in the lab. So we have some circuit like this sort of any test circuit. And notice that we have it connected to some load over here. So we'll just call that resistor a load. And we're allowing that circuit's current and voltage to pass through this resistor. So if we were to change the amount of current or voltage being supplied across that load, we could monitor this circuit's IV curve. We could determine how does that circuit's current and voltage behave over a range of conditions. And we would end up getting some result as shown. Notice that there's these two parameters here, VOC and ISC. So these define the intercepts of the IV curve with the x and y axis, or vertical horizontal axis. And notice, since the circuit has linear behavior, the IV curve is a line for linear behavior. Okay, so let's talk more about what's so special about open circuit voltage and short circuit current. Well, open circuit voltage, VOC, is the voltage at the circuit's terminals when current is 0. So basically, it's similar to having a circuit where, notice if we had like 5-volt source, 10-ohm resistor, here the open circuit voltage would be 5 volts because there's no current across the 10-ohm resistor. It's open, so we're basically sitting at a 5-volt potential difference. So once again, open circuit voltage is the voltage we would see if there's no current flowing through our circuit. The other parameter to consider in this curve is ISC, the short circuit current. Short circuit current is the current that flows when our voltage equals 0. So ISC is the current that flows when there is no voltage across the terminals. And so if our voltage is 0, any current flowing through our circuit would be given by ISC. So why do we bother with VOC ISC? Well, we just saw that if we define these 2 points, if we know VOC and ISC, then a linear circuit will be fully defined by the line connecting VOC and ISC. So the circuit's behavior across any range of input currents and voltages will be governed by that line. So if we have a linear circuit and we know VOC, ISC, then any other linear circuit that also has the same, any other circuit with the same VOC and ISC is equivalent because it will have the same IV behavior. Remember, if you're a voltage source or if you're a circuit, you're not going to be able to tell the difference between two 5-ohm resistors in series and one 10-ohm resistor in series, because they're both equivalent. And that's basically what we're saying here. If we have two circuit elements that have the same IV characteristics, same current voltage behavior, then those are equivalent. So this can apply both to electrical components as well as whole circuits with sources. All right, so let's go ahead and return now to equivalent sources. Just as we said, if we have two sources and they have the same IV behavior, then the sources must also be equivalent. So basically, if we want to make a voltage source with series resistor equivalent to a parallel resistor and a current source, we would need to make the VOC and ISC equal. And we can show that a voltage source with a series resistor will be equivalent to a current source with a parallel resistor if these conditions are met. So you can see that the voltage source of the series resistor must be equal to the parallel resistor times the parallel current source's current. That would make ISC equal for both the voltage source and series resistor and the parallel resistor with the current source. Similarly, we would need to have the two resistors be equal in magnitude in order to make those values match. If you're curious, you could go ahead and try calculating this using the open circuit voltage and short circuit current, and you would in fact see that these relationships would emerge. All right, so that finally leads us to source transformation. Based on what we learned about IV curves, we have therefore shown that it is legal to replace a voltage source with series resistor we can replace that with a current source with parallel resistor. But in order to replace them, we need to make sure these conditions are met. So these conditions must be met in order for the circuits to be equivalent. So in order for the IV behavior to be the same. Notice the fine print here. Remember, we have to set the variables to the values specified by these relationships in order for the circuits to be equivalent. And remember, this relationship only holds true for circuits which contain linear components. Again, that is generally 99% of the time correct for this class. But if you take more advanced circuits courses with nonlinear components, you may need to use other approaches instead. So now let's go ahead and do some examples showing how we can actually use this source transformation. Let's try one example here. Suppose I wanted to replace circuit A with circuit B. How could I determine IP and RP so that circuits A and B are equivalent? Remember, if I want to do a source transformation, I must maintain the relationships shown. Take a moment and think about it. Let's go through this together. What do we have? We know our series voltage is equal to 5 volts, that's Vs. We know the series resistor is equal to 10 ohms. What do we want to determine? We want to determine our parallel resistor, and we also want to determine the required current from the parallel current source. Let's first consider the resistor. What would our parallel resistor need to be in order to satisfy the equations shown? This is actually one of my favorite equations we cover in the class because it's so simple. By source transformation rules, the series and parallel resistors must be equivalent resistance. They must be equal resistance values, so that means our parallel resistance must also be 10 ohms. How about our current source? Well, if we look in our equations, we see that our parallel current source is given by Vs divided by Rs. Well, we know both of those. That's 5 volts divided by 10 ohms. So that gives us 0.5 amps. So therefore, we determine current source 0.5 amps, and our resistance is 10 ohms. Let's try another example. If you'd like, you could pause the video and try it on your own. Otherwise, let's do it together. Here we are asked to determine Vs and Rs so that circuits A and B are equivalent. So notice, what do we know in this case? Well, in this case, we know that IP is equal to 3 amps, but hey, wait a minute. Notice that this IP is pointed downward. But in our figure, our source transformation rule required the polarity to be opposite. So notice this orientation. We can equivalently write that this circuit is the same as a 20 ohm parallel resistor and negative 3 amp current source, with that current source pointing upward. So be careful of the direction. It turns out our parallel current is actually going to be equal to minus 3 amps if the source is oriented in the same way as our picture. We also know that our parallel current is 20 ohms. So what do we get for Vs in this case? Well, we know that Vs is equal to Rp Ip, so that gives us 20 ohms times negative 3 amps. So Vs is going to be negative 60 volts. So watch the signs there. And then what will our series resistance be? Well, we know the series resistance must equal the parallel resistance, which was 20 ohms. So series resistance must also be 20 ohms. So there you have it. Again, be careful of the orientation of sources when you're doing source transformation. Notice you want the polarity to be oriented with positive facing up, and you want the current arrow to be pointing upward. If your directions are opposite that, then make sure you multiply by -1 to account for the opposite orientation. All right, let's try one more example here. Remember we said the reason why we're learning source transformation is to make our lives easier. Let's consider this circuit. This circuit's a little bit ugly, right? Question asks, how can source transformation make this circuit into a single loop? And when I say single loop, I mean something like this. So notice there's no more parallel resistors inside there. So that would make the circuit a lot easier to analyze, wouldn't it? Let's think about how source transformation could simplify this circuit. I'd encourage you to try pausing the video and think about it, and then we'll do it together. Okay, well, my goal is to turn this circuit into a single loop, right? Notice the 6 ohm and 12 ohm resistors, these are in parallel. So the first thing I can do is let's combine those to get a single equivalent resistor. So if we do that, notice what we get. So here, this single equivalent resistor is given by the 6 ohm resistor in parallel with the 12 ohm resistor. And remember, that's simply 6 times 12 over 6 plus 12 ohms. If we use our shortcut, that's 72 divided by 18. That gives us a resistance of 4 ohms. Okay, so now there's just one resistor in that portion of the circuit. And notice here, now we have a current source with a parallel resistor. Well, wait a minute. We can do a source transformation, right? So notice by source transformation rules, we can do this. We can take that current source and parallel resistor and change it. So again, if we just consider that portion of the circuit, we can change it. We can change that circuit to a voltage source and series resistor. So notice we know that our parallel resistance is 4 ohms. What's our parallel current, IP? Notice the source is pointing downwards. So if you want, you could also consider this if you prefer to have the current source upright. Let's just call it negative 4/3 amps here, so that we can replace it with the voltage source in the correct orientation. Well, we want to know our series resistance, and we want to know our series voltage. And how is our series resistance related to that 4 ohms? Remember, series resistance must equal the parallel resistance. We also know series voltage is just parallel resistance times current. So we know series resistance will be 4 ohms. Series voltage will be IPRP, which is equal to 4 times negative 4/3, which is negative 16/3 volts. So if we perform those substitutions, notice we get our circuit in a single loop. And here we have negative 16/3 volts. We have our RS value, which is 4 ohms, and then we still have the same items on the other side. So there you have it. So again, be very careful here of orientations and signs. So notice I drew my voltage source with the positive terminal oriented on top, so I did need to consider my current source in that same desired orientation in order to maintain polarity. I could alternatively have written this as 16/3 volts, but with the voltage source inverted. All right, so that concludes our discussion of source transformation. Notice it can be incredibly helpful to replace a voltage source and series resistor with a current source and parallel resistor. And notice we can also go in the reverse direction as well. Let's move on to superposition. So superposition, by definition, tells us that the response of a linear circuit to several inputs working together, that response is equal to the sum of the responses to each input working separately. Let's look at an example here. So suppose I had a resistor connected to 2 voltage sources. I could say by superposition I could say that this circuit behavior could be given by the sum of circuits with the resistors operating separately. So in this case, the voltage across resistor R1 would be equal to the voltage across R1 with V1 only, plus the voltage across resistor R1 with V2 only. So in this quick example that I drew, it doesn't look very helpful because, it's very easy to see the relationship. But imagine if you had a circuit with 3 or 4 sources. And imagine if the circuit was much uglier. Superposition allows us to consider a circuit with multiple sources and break that circuit with multiple sources into a circuit with just one source at a time. Then we take the algebraic sum of the responses and we can find the total behavior of that circuit. Let's look at the definition one more time. So once again, we say in any linear circuit containing multiple independent sources, notice independent here, the current or voltage at any point in the circuit can be calculated as the algebraic sum. We can take the algebraic sum of the individual contributions from each source acting alone. Here's a more detailed example. Suppose I have a circuit that contains both a current source and a voltage source. If I wanted to find VR4, notice what I could do is I could consider the circuit with the current source alone, plus the circuit with the voltage source alone. And notice I solve for the voltage across that resistor in both cases, and I can sum. I can take the algebraic sum of the voltage across those resistors with each source alone, sum them to get the total voltage across the resistor with both sources combined. The key thing you want to make sure you pay attention to is that to turn off a voltage source, you replace it with a short or a plain wire, and to turn off a current source, you replace the current source with an open. So you want to make sure you follow this procedure very carefully so that you don't accidentally make mistakes. Let's go ahead and review our procedure, and then we'll do some examples of superposition. Here's the procedure that I recommend you follow. First, you want to draw the circuit with each source considered separately. And again, you do this for each of the independent sources. So what you do is you turn off all the other independent voltage sources by replacing the voltage source with a short. So remember, a short has 0 volts. It's the same as a plain wire. And then you'll see for the current sources, you replace the current source you want to turn off with an open. Remember, an open has 0 amps current, like a broken wire. So please make sure you remember voltage sources are replaced with a short, current sources are replaced with an open, and notice any dependent sources are not changed. Only independent sources are replaced. Once you have turned off all the other sources you don't want, then you calculate the contribution of each voltage or current source alone to that desired output parameter. So we saw in this example here, we consider current source alone, and we see how much voltage do I get if only the current source is present. Similarly, I calculate how much voltage I get across the resistor with only the voltage source present. To do these calculations, we want to use the tools in our toolbox. Often things like voltage division, node and mesh analysis, and Ohm's law and equivalent resistors. So you want to use the tools in our toolbox to find the contribution from each source. And finally, once you have found the contribution from each individual source, you take the algebraic sum in order to determine the total impact of all the sources on that component of interest. So we see in this case, we can take the contribution from current source alone and voltage source alone and sum them to get the total voltage produced by both sources. Let's go ahead and try an example. Superposition might seem intimidating at first, but you'll see that once you do a few practice problems, it'll become a lot easier. Also remember that superposition is a really great way to practice some of the other circuits tools we already know. And often it's a very good exam question to write because you can test both ability to understand superposition as well as ability to understand other circuit tools. So let's consider superposition for the circuit shown below. Our goal is to find the current IA. So let's start with our first step. In our first step, we want to draw both versions of the circuit with the voltage and current sources removed. So we need to draw two circuits. One circuit that has only voltage source, and then the current source is replaced with an open. And then we have a second circuit that contains only the current source and the voltage source replaced with a short. If you'd like, you can pause the video and try this yourself. Alright, so with the voltage source alone, notice we still have that 8 volts in there. We still have the 6 ohm resistor, but notice our current source is replaced with an open. And remember, our dependent sources aren't changed. So in this case, our dependent source is going to depend on, let's call it IA1, because remember, this is just the contribution from our voltage alone. So we say that IA total is IA1 from the voltage alone plus we have IA2 and IA2 is the contribution from the current source alone. So there's our first circuit that we draw, and then in the second circuit, notice we instead turn off our voltage source, and we leave in our current source. And notice once again, for our current source alone, we have current IA2 going through our 6 ohm resistor. So make sure you're able to reproduce these results. Remember, the voltage is replaced with short, and the current source is replaced with an open. Let's go ahead and label that. Okay, so if you did this properly, you should have ended up with some circuits like this. Make sure you know how to draw these circuits, and if you're doing homework or exam problems, make sure you show this step. Often, if I ask about superposition on an exam question, part of the question will require that you draw the two circuits alone. So definitely draw these. That way you can at least get partial credit for your solution to superposition questions. Okay, so the next part of superposition is we need to find the contribution of each source alone to that desired output. So here we want to find IA1 and IA2. Remember, IA1 is the contribution to IA from the voltage source alone. IA2 is a contribution to current from the current source alone. So let's start with our first circuit here. So question becomes, how can we find IA1 in this circuit? What tools in our toolbox do we have that we could use for that calculation? Take a moment and think about it. How about Kirchhoff's voltage law? Notice we know that the sum of the voltage rises and drops must be 0. So we can write a Kirchhoff's voltage law equation. Kirchhoff's voltage law tells us that we have plus 8 volts minus the voltage across our 6 ohm resistor minus the voltage across the 3 ohm resistor minus the voltage across our dependent source, which is 3 IA1. That must sum to 0. That we can also write this as 8 volts minus 6 IA1 because the 6 ohms is IA1 times 6 ohms, right? By Ohm's law. And similarly, voltage across the 3 ohm resistor is IA1 times 3 ohms. So notice we can determine in this case 8 minus 12 IA1 is equal to 0. Interesting, right? Because notice we can solve for IA1. And if we do this, we determine 12 IA1 is equal to 8. So IA1 is 8 divided by 12, which is, by common denominator, equal to 2/3 amps. That wasn't so bad, was it? The key thing here was recognizing what tool you could use to determine that current IA1. Keep your toolbox handy, because often just by looking at all the equations we know, a tool might come to mind. If you didn't immediately recognize Kirchhoff's voltage law here, that's okay, but keep practicing. You'll find that the more you practice questions like this, the stronger your intuition will be, and you'll improve at recognizing which tool to use. You might also have thought to use mesh analysis, because by looking at this circuit, you see that there is just one mesh or one loop for current to flow through. And so being able to recognize that you have just one mesh might have led you to decide to use Kirchhoff's voltage law for convenience. Okay, so we found the contribution to current from our voltage source alone. Now we need to do the other one. So now we need to find IA2. Do you notice anything special about this circuit? How about this? Notice the 2 amp current source is shared with 2 meshes. Right? Like if I wanted, I could actually define current IA2 in this left-hand mesh, and I could, let's just call it I1 in the right-hand mesh, and notice I've got a shared current source. I can write a supermesh equation. Another approach I could use node analysis and then eventually solve for IA2. So either of those approaches would work. I'm going to go ahead and use the supermesh approach. I'm going to go ahead and use a supermesh along the perimeter of my 2 meshes. So I'm going to apply Kirchhoff's voltage law to my supermesh. And what do I get? I get minus the voltage drop across the 6 ohm resistor, minus the voltage drop across the 3 ohm resistor, minus 3 IA2. It's the voltage across that dependent source. Those must sum to 0. And again, I know that the voltage drop across my 6 ohm resistor is just 6 ohms times IA2. So I get minus 6 IA2. Notice the current going through my 3 ohm resistor. Notice I also have this 2 amp source coming in, and I have IA2. So be careful that you correctly determine the current at each point along your super mesh. Here I determine that my voltage drop across that 3 ohm resistor must be minus 3 ohms times IA2 plus that 2 amps. And then I finally have another minus 3 IA2, and everybody sums to 0. Notice in this case I have one equation and one unknown. So I can go ahead and simplify. So I just go ahead and distribute everybody through. And notice I end up with minus 12 IA2 equaling 6. So IA2 is going to be equal to minus 1/2 amperes. So it's kind of cool, right? We get to apply different circuit tools depending on our circuit. This second circuit required a supermesh, while our first circuit required Kirchhoff's voltage law. So you want to be comfortable using all different types of tools when solving superposition problems. So if you perform the calculations correctly, you should have determined that the current IA1 is 2/3 amps, IA2 is minus 1/2 amps. Remember, the total current IA must be equal to the algebraic sum of IA1 plus IA2. So now that we know IA1 and IA2, we can determine that IA is equal to, in this case, 2/3 amps plus negative 1/2 amps. If we math that out, that's going to give us a total of 1/6 amps for IA total, with both sources combined. So there you have it. I highly recommend that you go back through this example and try it yourself. Verify you're able to get the same result that I did. One of the best ways to get comfortable with superposition and all these circuits is to do examples on your own. Let's try one more example before we wrap up for today. Suppose we have this circuit. Notice that this circuit has 2 voltage sources. We've got 2 voltage sources. And you might be thinking, oh my goodness, this one is time dependent. But notice that the behavior is otherwise still linear. It just happens that the exact value is changing with time. But again, we don't have any nonlinear components in this circuit, so superposition can still be used. Let's go ahead and apply superposition as we just learned. So remember, our first step is to draw the circuit with each source considered individually. So we consider each source separately. And remember, the extra voltage sources is replaced with a short. Current sources are replaced with an open to turn off the unwanted sources. So in this case, we have 2 voltage sources, so we will just replace the other voltage source with a short. So here's what we get. For the 12-volt source alone, we've got our 12-volt source, still have the 40 ohm resistor. I'm going to call this V1 of t. We got our 10 ohm resistor. And notice the other voltage source is replaced with a short. For the 12 cosine 5t source alone, same approach, but this time the 12-volt source is turned off. And notice we are left with 12 cosine 5t as the only source in our circuit. And remember, by superposition, we know that V of t from both sources must be equal to V1 of t plus V2 of t. So our next step is to find V1 of t and V2 of t, and then take the algebraic sum. So let's start with the 12-volt source alone. Let's find V1 of t. How do we find V1 of t for this circuit? Take a moment and think about it. You might also find it helpful to redraw the circuit slightly. So if you're ever not sure, this is not a bad strategy. Notice I can draw this same circuit like this. And I know that my voltage across both of these resistors must be the same because the 40 ohm and 10 ohm resistors are in parallel when the other source is replaced with a short. So what should we do here? We want to find V1 of t. Well, how about we replace the 40 ohm and the 10 ohm resistor with an equivalent resistor. We know the equivalent resistor will be equal to 40 times 10 over 40 plus 10. That's 400 divided by 50 ohms, or 8 ohms, right? So therefore, our circuit will become 12-volt source, and now we have an 8 ohm resistor and a 40 ohm resistor in series, and we want to find V1 of t. V1 of t is now the voltage across what were my two parallel resistors. Now it's just the voltage across the 8 ohm resistor. What do we do now? How about voltage division? Remember, voltage division will tell us the voltage across a resistor in series. So we know that the voltage across our 8 ohm resistor is going to be equal to V1 of t, which is going to be equal to our 8 ohm resistor divided by the sum of the resistors. Right, so 8 ohms divided by 40 plus 8 times Vs, which here is 12 volts. So what does that give us? That gives us 8 divided by 48 times 12 volts, or 1/6 times 12 volts. So that means V1 of t is equal to 2 volts. That wasn't too bad, right? Notice how recognizing whether resistors are in series or parallel can really help simplify your circuits. Here, by recognizing the 10 ohm and 40 ohm resistors were in parallel to each other, we were able to more quickly and easily find V1. Let's now repeat the process with the other voltage source alone. So now we want to find V2 of t for the 12 cosine 5t source alone. So now our circuit looks like this, right? Got our 40 ohm resistor, V2 of t across the other 40 ohm resistor. We've got our 10 ohm resistor, and now our voltage source is on the right-hand side. How do we approach this one? If you're thinking about doing the same approach as before, you would be correct. We can once again combine the parallel resistors. So in this case, the parallel 40 ohm resistors. And then find V2 of t using voltage division. So let's see what we get. Some students find it helpful to redraw this circuit, so I'm just going to quickly redraw it in a way that makes it easier to see. So notice, walk along this circuit. I first see that 10 ohm resistor, and then I have the choice of going through one of two 40 ohm resistors. And both of these resistors are in parallel, so they would experience a voltage drop of V2 of t. So in this case, the parallel resistors, that's just going to be 40 times 40 over 40 plus 40, right? Using our shortcut equation. That ends up giving us 1600 ohms up top, divided by 80 down below, or 20 ohms. So our circuit now becomes something like this, right? We now have our 10 ohm resistor, and then we have a 20 ohm resistor with voltage drop V2 across it. And remember, our voltage source is given by 12 cosine 5t. So once again, we can apply voltage division. We can find that V2 of t is equal to the voltage drop across our 20 ohm resistor, which is 20 ohms, divided by 10 plus 20, times our source, which is 12 cosine 5t. That's also equal to 2/3 times 12 cosine 5t, which is equal to 8 cosine 5t volts. Once again, just take it step by step. At the end of the day, superposition is just breaking our circuit down into circuits with individual sources and applying the tools we already know. And so, if we've completed this correctly, we will find our two circuits and we determine that our total voltage is the algebraic sum. We end up getting our voltage is 8 cosine 5t plus 2 volts. All right, so let's go ahead and wrap up here for today. So in summary, by now you should be able to source transformations to help simplify and analyze circuits. Also, make sure you get comfortable with superposition. And make sure you practice using superposition as a way to more easily analyze circuits that have multiple sources. And remember, both source transformation and superposition require circuits to be linear. So make sure you remember how to determine whether circuits are linear. For the purpose of this class, 99.9% of the time we're going to be linear. But if you take future courses, you want to make sure you're aware of when circuits may not have linear behavior. So thanks everyone for joining the fun, and please do feel free to reach out if you have any questions on this. Thanks everyone, and we will see you in the next video.